Okay, and then okay, so here I'm not going to present any new results or something like that. So it's just somehow to share with you what I learned about the collision term. So this actually is some things I was thinking about when I was here in Vienna some years ago. And it was just about understanding, well, how can one derive the collision term also in terms of these geometric tools I told you about, or say in a way that is covariant, I mean, without somehow introducing coordinates or going to a coordinate chart or something like that. And basically I want to share with you what I've learned here. So this is, I guess, especially going back to the course philosophy, and supposed to be pedagogical. And towards the end of the course, then, I mean, I will show you also some standard things that you do with the Boltzmann equation, the Boltzmann H theorem in the relativistic case. And I will try to point out some interesting things about the relativistic case, especially the general relativistic case, okay? So we're going to finish a little bit about the question of what is thermoequilibrium when you have a curved spacetime. All right, so so far what we have done, if you remember what we did 2 days ago, so we formulated the theory for a collisionless kinetic gas, relativistic kinetic gas, charged or uncharged. So that means the particles, they only interact between themselves indirectly. So they interact themselves through the electromagnetic field or the gravitational field. But if you have short range interactions between the particles, then you need to take this into account, okay? So this could be collisions, okay? Or you could think also in terms of close encounters. If you have, for example, 2 stars in a galaxy and they come very close together, then you can look at this like an effectively a collision, if you want. Okay, and so what we're going to do, we're going to analyze to look at ideal collisions in the sense that we're going to assume that they are point-like, so they're taking place only at one specific event. So that means before they encounter each other, their path is not modified. So they follow the Liouville vector field, and then from then on, I mean, sometimes there are collisions, and then when a collision occurs, and somehow the momentum is redistributed. Okay, but it takes place at one specific event. I mean, at one event in space-time. The collision is not blurred or something like this, okay? Further, we assume that the gas is dilute enough such that it is sufficient to consider binary collisions. We are also going to use later this diluteness to impose Boltzmann's molecular chaos hypothesis, but that's later on. And finally, we are going to assume that the collisions are elastic, so energy momentum is preserved. Okay, so what does that mean? So, okay, and let's focus also on the case where there is no charge for simplicity. In the article, we do it with charge, I think. And also that the particle is identical. So what we have to do then is to understand the set of all P1, P2. So these are the collisions, the momenta before the collisions, and P1 star, P2 star, the momentum after the collisions, which satisfy this equation. So that looks like a very simple equation, but it is deceitful because P1, P2, P1 star, and P2 star, they each live in this future mass hyperboloid. Okay, so this is really a nonlinear set because of this condition here. Now, for what follows, it is very useful to introduce the relative speeds. So this is, so here's a little diagram. So you have P1, P2, here is a collision, then you have P1 star and P2 star, outgoing momentum, and then Q is the difference between them divided by M, and Q star is a P2 star minus P1 star divided by m. Okay, so these are the relative speeds before and after the collision. And then you have the center of mass moments. So this is P1 plus P2. But now you divide by this factor here. And this is done so that PCM is on the mass shell again. So this is a normalization to guarantee that this behaves like a particle of mass m. And this again, you can define before and after the collision, but that's the first exercise of this part. So show that these relative velocities, they have the same magnitude. Okay, so that implies that the center of mass moment before and after the collision is the same. Okay, so you can show that this is a correct normalization. And furthermore, you can show that Q and Q star, they are orthogonal to PCM. Okay, and now you have a nice way to parameterize your collision. So instead of giving P1, P2, P1 star, and P2 star subject to these conditions, you can as well specify PCM for the center of mass momentum, which is a 4-vector or covector on the future mass shell. And then you specify 2 orthogonal vector Q and Q star, which have the same length and are orthogonal to PCM. Okay, and then that's the inverse formula if you want. So if you give PCM Q and the absolute value of Q, then you can reconstruct P1, P2, P1 star, and P2 star. Some other useful variables you can introduce is the scattering angle. Okay, so that's just the angle between Q and Q star. I mean, they are both orthogonal to PCM. We can think of them in free space. And then there are the Mandelstam variables, which are these free Lorentz invariant contractions. And that's, I couldn't resist to put this next exercise because it's nice. So if you denote by G the absolute value of the velocity, then you can express these free Mandelstam variables solely in terms of G and M, of course, and then the scattering angle. Okay, so actually only 2 of them are independent. If you sum the free up, you get 4m squared. Okay. Well, and that's actually expected. So you have 4 momenta. So you can take 10 products, 10 Lorentz products between them, but 4 of them are just a mass shell condition. So that's determined by m. And then you have 6 left, but you also have the energy momentum conservation, which are other 4 conditions. So you have 2 degrees of freedom, basically, which are encoded in theta and g in this Lorentz invariant quantity. Okay, and then here's a definition. So then you define the collision manifold. So this is this 4 tuple of P1, P2, P1 star, P2 star, each on the mass shell, which satisfies this condition. And here it is important actually to demand that P1 should not be equal to P2. I mean, physically that would not make sense to have P1 equal to P2 because it's a collision at the same place, right? So that would mean a particle colliding with itself somehow. So, and actually you have to take this out if you want to show that this is a nice smooth manifold. And then you can show this manifold is an 8-dimensional submanifold of 4 times the future mass hyperbolic. And the topologies are 4 cross S2 cross S2. Okay, and this is the next exercise. All right, and then we can consider the associated bundle. So you add X to it, basically. So X in M, and then over M, you have one of these objects here in CX. All right, and now there's an important theorem. It will be very important for later. So you can ask the following question. So if you have a function on the future mass hyperboloid, which is, say, continuously differentiable, and you require that this F is a collision invariant. So the collision invariant means it preserves the energy momentum conservation. So F of P1 plus F of P2 is equal to F of P1 star plus F of P2 star for all points on the collision manifold. Okay, and you can show that this is true if and only if f has a following form. So it's a constant plus something that is linear in P. So P contracted with some vector beta. Yes?
You don't consider the kinetic energy?
Because it's relativistic. So yes, so the Newtonian analog would be, you have momentum, so you have free momentum, and then the kinetic energy would be P squared. Yes. So this is a relativistic generalization. So you have four conditions, which are this. Yes. This is built in here. Yes. This is built in through the mass shell condition. So if you look at the zero components, really, that would be, square root of m squared plus p1 squared, and so on. That gives you the nonlinearity. All right. Okay, so the if part is obvious. So if f has this form, then clearly if alpha, if you have the constant here, we just drop out, and this linear term obviously satisfies this. But the difficult part is to show the converse, but it's already late. So I'm just giving you the idea. So one way of proving this is that you look at p to the 4, so the mass hyperboloid, the 4 copies of that. So this function takes now these 4 momenta and just gives you fp1 plus fp2 minus fp1 star minus fp2 star. So this function by definition is constant on Cx, it's 0 on Cx. Okay, that means that this gradient must be orthogonal to Cx, which we know is a nice manifold. Now you just write down what are the normal vectors to Cx. And then you will find that the differential of f should be some coefficients times dp alpha. And now you have to show that these coefficients are independent on p. And once you've done that, you integrate this equation and you get this. So that's the idea. Okay, and now 2 other things we're going to need about the collision manifold. So the one thing is that you can compute the induced metric on the collision manifold because you have a metric on the mass hyperboloid. So you can compute from this metric actually on the collision manifold, and from this a volume form, and here it is. So this is a tough calculation, so I didn't put it as an exercise, but you can find it in the article. Okay, so basically you have so it's 8-dimensional, remember. Okay, so here you have 3 from this Lorentz invariant volume element. Here you have 3, and this is Q hat star here. So these are the components, if you want, of the relative velocity in the center of mass frame. So these are, if you remember, these are just 3. This has just 3 components, okay? But furthermore, the normalization is equal to G, which you can compute from P1 and P2. So this really, so this is the direction really of this Q, okay? And this is just the spherical element associated to it. Okay, and S and T and U are the Mandelstam variables. Now, the collision manifold possesses the following discrete symmetries. So if you interchange P1 and P2, or P1 star and P2 star, so this leaves it invariant, of course, but also if you interchanged P1, P2, the pairs P1, P2 with P1 star and P2 star, that's also leaving all these objects invariant. All right, so now we come to the closer to the collision term. So now I introduce the transition probability density. Okay, so this is a function from this bundle here, T star C to R. Okay, and we are going to require that it is invariant with respect to J and J star. Okay, because if I interchange P1 and P2, that's really just because the particles are identical. I'm not doing nothing. So this should be symmetric with respect to that. And then giving a neighborhood in this collision bundle. Okay, which is symmetric here. So the interpretations are when you integrate over the collision manifold and M, and u actually. So here I put the characteristic function of u. Okay, so this integral here, that gives you the average number of collisions that have x, p1, p2, p1 star, p2 star, and u. Okay, so that if you want, that measures the number of collisions that have these properties. Now here I put, if you look at here, I put the distribution function here. So really this should be the two-particle distribution function that you put here. But here comes in now the molecular chaos hypothesis by Boltzmann. Okay, so we assume that just before the collisions, the particles are not correlated. So you can replace the two particle function by the product of the one particle distribution function. Okay, so that's central because otherwise you don't get a closed system. But this is now where this comes in. Okay, so this is what this transition probability density will measure for you. Okay, we are also going to impose macroscopic reversibility. So that just means that this transition probability density should be also invariant with respect to the K symmetry. So the K symmetry, if you remember, that interchanges the ingoing particle with the outgoing particles. And actually you can check that this is a consequence of Lorentz invariance. I mean, as an exercise, you can check if you apply, so N is like the vector that connects Q and Q star. Okay, and now you can check if you make a reflection by a plane orthogonal to N that will interchange P1 and P2 and P1 star and P2 star. And you can check also this is a Lorentz transformation. So if this is Lorentz invariance, I mean, if you impose Lorentz invariance, then this macroscopic reversibility will be automatically satisfied. All right, now let us come back to the, let us go towards the collision term, derive the collision term. So for this, I'm going to recall this identity from 2 days ago. So you remember, we are in the phase space or in the future mass shell. We took a 6-dimensional surface here. We let it flow along this current here, okay, until some time. Then we get this blue region here, which is V. Okay, and then the number of occupied trajectories here minus the number of occupied trajectories here was the volume integral over the divergence of J, but the divergence of J was 1 over M times L that acts on F. Okay, so if the gas is collisionless, that gave us the Vlasov equation. But now we want to take into account collisions. So what happens when you have collisions, then the number of occupied trajectories may change. And how does it change? Well, there are different scenarios. So here again is this blue region now with a slightly different orientation. So sigma 0 is here, sigma 1 is here. So now here, what might happen are different things. You could have initially two trajectories that are occupied here, but at the point X, they will collide. Okay, so these are two trajectories that go through the same fiber, so they have an encounter here in space-time. But then they suffer a collision, and then what might happen is that after the collision, P1 star and P2 star are outside this tube. Okay, so this is described by this set here, and as such a collision will lead to a depletion of the average number of occupied trajectories by twice the average number of such collisions, right? In this tube here. Okay, twice because you started with 2 particles inside and then you have 2 particles outside them. So when you get here, you have 2 less particles. Now you can go through all the scenarios. Another scenario, you have particles colliding, but after the collision, one is still inside and the other one is outside. So that just gives you a factor 1 here. And here's another possibility. So you could have initially both are outside, but then they collide here, and then one is inside and one is outside. And then you just go through all the 9 possibilities. And in general, if you denote by Uij, the set of collisions where you have I incoming particles inside V and J outgoing particles outside, inside, also to V after the collision. Then the net change is just J minus I times this number here. And by doing this, now you can write this difference explicitly. So this difference is just, you just sum all the possibilities that you have. So these are 9 possibilities, but 3 of them, they give you 0 difference. So I didn't put them here. And this is actually the Boltzmann equation, the relativistic Boltzmann equation in integral form, integrate over the phase space. But to get the usual form, so what you can do, you work out this right-hand side. And if you do that and you use the symmetries that we have imposed over W, then you can boil it down to this expression. The 1/2 the integral over mcx. Then you have the transition probability here and here. Well, this is the usual notation. So F1, just to abbreviate, is f of x p1, and f2 is f of x p2, and this is the same with the star. Okay, so this right-hand side you can write like this. For the left-hand side, yeah, but the left-hand side we could write also. The left-hand side we can write. I mean, we can write as this integral here. Okay, so both have to be equal, and that holds for any sigma 0. So now you compare the integrals. You compare the integrals, and then what you get out is this result. So here you have the Liouville operator acting on F, and here you have this collision term, and the collision term is basically everything you had except the integral over. I mean, you have to use the result about the volume form that we had, so that gives you a multiple integral, and then you compare the integrals on the left and the integrals on the right, and then you get this expression here. Okay, that's the collision term. You can rewrite the collision term that we try also to explain in the article. In terms of the differential cross section. So instead of having this transition probability, you can put it in this way here. So here you still have the same thing. This factor now is absorbed in the definition of the differential cross section. And then you have this factor here, which is called invariant flux. And this you can rewrite if you want as in a very nice way. It's just the product of the incoming momentum squared minus m to the 4th and the square root of that. Okay, and that's really cool because now if a particle physicist gives you the differential cross section, then in principle you can put it here, and now you can look what happens to your gas. Okay, so the integral is still 5-dimensional. So you have 3 dimensions here of the mass shell over P2, and then here you have an integral over S2. All right, so now to I mean, to see that everything goes fine, like we had in the collisionless case. So now what you can do, you can show that the current density and the stress energy tensor are still divergence free, and you can do it in the following way. So you multiply both sides of the Boltzmann equation by some function psi and integrate over P. And on the left-hand side, you get this. On the right-hand side, you get this. And again, you use the symmetries of W. You can rewrite it in this way here. Okay, and now you see from this formula that the right-hand side is 0 if psi is a collision invariant. So if psi, for example, is constant, then this goes away. And then you will get the integral of LF d vol P1 is 0. Now, if you remember proposition 7, that was exactly the condition that allows you to conclude that the divergence of J is 0. Okay, so this is automatically satisfied for a solution of Boltzmann's equations. Similarly, if the other collision invariants are just components of the momentum, okay, because of energy momentum conservation. So if this is proportional to P, this also goes away. And you have here P mu L d vol. And if you remember, this was the right-hand side of what you had in proposition, of what you had in the gradient of T mu nu, this identity in proposition 7. Okay, so this is fully consistent and allows you then to couple the Boltzmann equation to the Einstein equations and consider the, should I call it Einstein-Boltzmann or Boltzmann-Einstein equation? Which one is more difficult? Yes. Yes. Okay, yes. All right. And now there's a new thing that you don't, that is really where the collision gives you something new, where you have something interesting that is happening. Now you can also choose psi equal to 1. Well, the 1 is just for make the calculation simpler, but you choose a log of f. So a is just a constant because f is not dimensionless. So should put here some constant, some dimension, full constant a here. And if you do that, then you don't get 0 on the right-hand side. So we'll get log f1 plus log f2 minus log f1 star log f2 star, but then you use the properties of the logarithm. And then you see you can, and the symmetries of W, and then you can write it in this way here. On the left-hand side, now you will have the Liouville operator that acts on 1 plus log f. And that gives you what is called the entropy flux. So that will give you the divergence of the entropy flux if you use again the identity from the proposition. But the interesting thing now is that this has a sign. Okay, so this is actually positive definite. This function is positive definite, but it's of the form x minus y times log x minus log y, and because the log is an increasing function, so this is positive definite. And hence you get the second law of thermodynamics, if you want. So you get a non-increasing entropy flux. So now if you integrated this, over Cauchy surfaces in asymptotically flat, globally apolog space-time or something like that, you would actually see that you have a direction where the entropy, increases. Sorry, it should say non-decreasing entropy flux, sorry. Okay, but now you can make another observation as well. So you can ask, when does this entropy, when is this 0? Okay, so what is, when you get to equilibrium? Okay, and this is 0 actually when f1, f2 is f1 star, f2 star. But this means that log f is a collision invariant. Now, by the previous theorem we saw, that means that f should be, the log f should be of the form a constant that might depend on x now because it's for it's pointwise, plus beta times p mu. And now if you take the exponential, this is what you get. Now what you recognize here, this is precisely a Eutner distribution function. Okay, so now you know where it comes from. Okay, so we have just shown that the Eutner distribution function is singled out by having a vanishing entropy production. And you can show that this also implies that the collision term, if you go back to the Boltzmann equation, then the collision term is 0. But if the collision term is 0, then the left-hand side, the transport part of the Boltzmann equation should also be 0. So in other words, the f should satisfy also the Liouville equation. Now, if you work this out, if you dot the Liouville equation on f, you will get this expression here. Okay, and this should, if you want this to be a solution of the Boltzmann equation, then this should be identically 0 for all x and p in the future mass shell. But now you see, this is a very strong condition because this is linear in p, so this should be 0, and this is quadratic in p, and you can show if p is time-like, that it implies that this must be 0 as well. So in other words, what this implies now is that alpha should be constant in x, and beta should be a killing vector field. And well, it better be time-like so that the integrals make a convergence on. Okay, so in other words, you see that now you get a very strong condition. So to have global equilibrium in a curved space-time, you need it to be stationary. Otherwise, there is no global equilibrium. So this is a very strong strong restriction. So in other words, if the space-time is not globally stationary, the entropy will always increase of the entropy of the gas at least. Now, if you take the massless limit, then it allows you a little bit more freedom, because if P is null, then this condition being 0 is still compatible with having a conformal time-like Killing vector field. So then it doesn't need to be time-like, but it's sufficiently be conformal time-like Killing field. That's interesting because it's compatible with the Friedmann-Lemaitre-Walker and Walker spacetimes. In this case, and if you have a gas of 0 mass, you can talk about global equilibrium still. But you need 0 mass. Yes?
Okay, the vector field beta should be time-like.
Oh, okay, so the time-like is because otherwise when you compute, the observables, it will not converge. So this should be, so that this is exponentially decaying for large P. Yes. Right. All right, so okay, now if you have the Newton distribution function, then you can also compute the entropy flux. And you will find that the entropy flux is proportional to the particle flux. And this is the entropy per particle you can compute. And the nice thing you can show with the previous definition of the temperature, the example I showed you last time, which was kind of formal, but you can show that this formal definition is actually a good one, because you get the first law of thermodynamics that kind of justifies this definition for the temperature in this case. Okay, now let me finish. So what do we do if the space-time is not stationary? So then people talk about local equilibrium, and I think here there's still a lot of work to do, but basically the intuition is the following one. So you can see, you make a rescaling argument, and it goes more or less like this. So the Boltzmann equation has basically two length scale associated to them. So one is the macroscopic length scale, which is defined, so I'm not going to try to define it precisely, but loosely it's defined as a length scale over which the macroscopic quantities vary in a significant way. Okay, so you can maybe associate it with a special gradient of some of your observables. And then there's a mean free path, which is like a microscopic length scale, if you want, so that you can define, say, by imposing this relation. So that's sigma t would be the total cross section and the particle density, and then you can, if you want, define this by this equation here. And now what you do, you rescale your variables in the following way. So you rescale x mu using this macroscopic length scale, p mu just by the mass. So all these quantities with a bar, they are dimensionless now. F has dimension, has this dimension here. So here you use also the macroscopic length scale. And here, based on this definition, so n has a 1 over L to the 3, which comes from the macroscopic length scale. And then you see that this should scale like this. Okay, and now all these quantities with a bar, they're dimensionless. So you rewrite the Boltzmann equation in terms of these dimensionless quantities. And what you see here is that you will find here, so you have again the Boltzmann equation, but in front of the collision term now you have 1 over Kn, where Kn is called a Knudsen number. So that's the ratio between the mean free path and this macroscopic length scale. Okay, and now you can look at different regimes. So you can look at what is called the hydrodynamic limit. So this is when the mean free path is very small compared to this macroscopic length scale. And this is the one where the collisions actually dominate. So you see if Kn goes to 0, then formally in this equation, this term will dominate. Or what you can think of. So you can think of doing an expansion, and that's what is being done in this Hilbert or Chapman-Enskog method. So you expand F in F0, now the Knudsen number times F1 plus Knudsen number squared times F2, and you plug this into the Boltzmann equation, and then to the zeroth order, I haven't written down, but to zeroth order, it is clear, just get that the collision term should be 0. But if you remember, this implies that F0 should be a Hüttner distribution function. Okay, only now you don't have, because this term is 0 now, you don't need this term to be 0. So you don't need global equilibrium. You only have locally that at every x it should be a Hüttner distribution function, but there's no requirement about the x dependency so far. Okay, and then at the first order you get this integral equation and so on. Okay, and then you can try to solve these equations. So I think there's still a lot of work to understand what this means exactly, but I would just want to point out that very recently there's been a paper in communication mathematical physics, so rigorous results for the special relativistic Vlasov-Maxwell-Boltzmann system, where they show that this Hilbert expansion actually converges. All right, so I'm just going to finish the last few minutes talking about problems. Also, the question is if it's possible to analyze a case without using this approximation, this hydrodynamic limit. So, like having an example where you can understand the solution, so what the solutions are doing if you are away from being close to local equilibrium. You have a question? Yeah?
You can find some hydrodynamics equation in this part?
That's right, yeah. So typically this Chapman-Enskog method that will give you back the Euler equation, and then gets a correction with viscosity and so on, yes. Yes. Okay, so and then there was a few years ago, there was a very nice paper by Basov and collaborators. So this was a physical review letters where they were able to find an exact solution of the full Boltzmann equation. For the full collision kernel, and then and I think that's a very nice model. And let me just tell you two things. One thing that's interesting that happens in this model. So what this is Friedman, Lemaitre, Robertson, Walker space-time, and you assume that the kinetic gas is isotropic and homogeneous. Okay, so that means you can show that the distribution function in this case depends just on two variables on time, and basically the norm of the momentum, okay, with a suitable factor A of t. So you can show that this is the only distribution function that is compatible with the symmetries. Okay, and then the whole system reduces to the Friedman equations, where you have the energy density and pressure given by these integrals. And then what you can do is to try to solve the Boltzmann equation using the method of moments. So that means instead of trying to solve directly for the distribution function, you multiply the distribution function with some basis of functions of the momenta and integrate them. Okay, and these are these pi s. I don't want to go into the details, but this is basically the integral over f times psi s is a suitable chosen basis functions. Okay, and then you can rewrite the Boltzmann equation in terms of this momentum, and here you have from the collision term you get like two terms. And the interesting thing, yes.
In turn, you said that they have a collision kernel explicit in some way. How have they chosen it? I mean,
Right. So the differential cross section for yeah. So what they have done, they have looked for at the limit of massless particles. This is a photon gas, and the differential cross section is constant.
Okay.
It's a hard sphere.
Okay.
That's right. Yes. Okay, and actually you can slightly generalize this, so you can look at the limit of this equation in the very early universe. So in the very early universe, when like the kinetic energy, if you want, of the particles dominates the rest mass energy, so you can just, it's like switching off the mass if you want, and then you are basically back in their case, and assume also that that you have a hard sphere kind of potential. I mean. A differential cross section. Interesting things is that in this limit, what you can show is that this moments equation decouples. You can decouple it from the Friedmann equation. So that involves like a separate system. And the system is very simple. So this is the system, and actually it's in hierarchical form. So you can solve first for s equals 0, then for s equal 1, then for s equal 2. So moments by moments. And then you can also show, so the equilibrium points here would correspond to all the m's equal 1. That's a solution to this. And you can, if you look just at the solution by inspection, you see that each moment decays exponentially to 1. So you would think that that equilibrium will be attained actually in this case. But there's a twist, an interesting twist to it, because this time tau here is not the physical time, but it's related to the physical time t by an integral of this form. This integral over particle density, and the particle density goes like 1 over the scale factor to the 3. So if the scale factor goes like square root of t, then typically this integral converges when t goes to infinity. So you see, it's funny because this wants to reach equilibrium somehow. But equilibrium would mean that tau would need to go to infinity, but tau cannot go to infinity because of this relation. So I wanted to end with this example, but I think this model might be a model worthwhile studying more. So actually the same thing happens also at the late stage of the universe. So in this case, you can approximate things using the non-relativistic limits. And at least for a Maxwell type differential cross section, you get exactly the same moment equation. So there is a model where at least you get some analytic handle in the very early stage of the universe and then the very late stage of the universe. So maybe, so I think this is a model that's worthwhile studying more. Okay, so I finish with this.